doing my talk on the reflections in nature. So a very obvious statement at the moment is that there's electromagnetic radiation all around us at this very moment. There's radio waves travelling through here, which allows you to check the internet and go on Facebook at the moment while I'm talking via Wi-Fi. At the moment, you are releasing thermal radiation, which could actually be measured in infrared. And then you've got visible light, which actually is responsible for our sense of sight. So in this huge spectrum of electromagnetic radiation, visible light only encompasses a very small amount of it. But that doesn't seem very significant, right? There's such a tiny amount. But when visible light actually interacts with matter, that's where you actually get to see the most interesting parts, phenomena and behaviour associated with visible light. And that usually produces optical phenomena, such as rainbows, caustics, iridescence, and also reflections, seen here. But for this talk, what I'll actually be focusing, obviously based on my title, is reflections, similar to what you see here. All right. So I should also say is that everybody knows about reflections. We've been taught it since year 10, so I'm hopefully will be able to explain it simply enough for you, because that was the whole aim of these talks. So when a beam of light strikes an interface between two mediums of different refractive indexes, the direction of the wavefront will actually change, so that some of the light is always reflected back into the incident medium. This phenomena is actually called reflection. There is also some refracted ray that is transmitted through the medium, the second medium, but for this talk, obviously, I'm not going to talk about it. The amount of reflection that is actually observed when you actually have light interacting with a boundary is actually dependent on how if it's a gradual change into a different refractive index. So if it occurs over a very long distance, like the change from 0 to 1 is very slow, the amount of reflection is very small. But if it's a very strong change, the amount of reflection is actually very big. The way to actually think about that is if I run into on a beach and run into the ocean, right, I'm going to be pushed back very slightly, but not going to be affected too much. But if I run really fast into a brick wall, obviously that reflects that I'm going to move backwards pretty quickly, right? That's how I kind of look at for this kind of thing. So, one of the most common ways that we actually observe reflection, obviously, everybody got dressed this morning and probably looked in a mirror. Exactly, that's reflection, the basic thing that we see all the time. So, if you could actually observe how light is actually approaching and then interacting and reflecting back with a medium, such as with using a laser, what you would actually get is that the behaviour will follow the law of reflection seen here. Obviously, everybody has seen this type of diagram where you've got the incident ray and the reflected ray, and then you've got the normal, which is perpendicular to the surface. And what the law of reflection actually states is that the incident angle is always equal to the reflected angle here. I have shown here the derivation associated with the law of reflection. Why can't I say that word? And it's based on basic geometric calculations and also Fermat's principle, which states that light follows the path of least time associated with it. So there are three main types of reflection that we observe in nature. There's diffuse reflection, there's specular reflection, and there's also total internal reflection. So a total internal reflection is when a light strikes a boundary between a medium at an angle greater than the incidence angle. And if the refractive index of the medium passed, like not its incident medium, the one that it wants to go into, is actually much lower than its incident medium, no light can actually pass through. So all the light will be reflected back into the incident medium. So it's kind of the opposite way. But in this talk, I'll actually just be focusing on light that goes from a lower refractive index into a higher refractive index. So what I will be focusing on is diffusive reflection and also specular reflection. So if you have All right, so obviously you have a beam that is made up of wavefronts, which when it enters the medium, it will actually change the direction. The type of reflection is actually dependent on what the surface is like. If the surface is actually quite rough, and what I mean by rough is that the variations in the surface is larger than the actual wavelength, what you actually get is this scattering of all those light beams coming through, right? Even though that they're still following the law of reflection, they will be pushed out into all different ways just because of how the surface is affecting it. Okay, here. So this actually causes a diffusive image, which scatters the light. And this is observed in nature, seen here. So when you look in reflections, you actually don't see a very clear image. It's very scattered and very diffuse in your image seen here. The other one is specular reflection. So the difference between specular reflection and diffusive reflection is that now the surface is very smooth. So when I say that the surface is that it's interacting is very smooth, is that the variations in the surface are much less than the actual wavelength of light. And this actually means that you will actually get very well-defined beams that will reflect off all at the same, like together, right? While, and they will all obey, so they will constructively interfere to produce this strong beam, which will all still follow the law of refraction. And this is probably, when you think of reflection in nature, this is probably the most common thing that you actually think of. When you look into a lake or something and you see wonderful images of the sky or some other reflection thing here. So, and it's always like the surface always has to be something like a mirror, for example, a very smooth lake that is not affected by anything, or somebody's sunglasses, or even a car thing associated with that. So normally when I see something like this, I always, especially because I like photography and I put a polarizing lens on, I've always wondered kind of how much light is from the, if I could only take the light that is reflecting off this lake, how much of that light is actually being reflected back to me? And the way that you can actually do that is by using the Fresnel equations seen here. This will actually allow you to calculate the fraction of light reflected from your boundary. And this proceeds by using boundary conditions at the interface of the media, seen here, the boundary conditions associated with the electric and the magnetic field, and then also from basic geometry. And the equations that you actually get are these horrible causes and etc. So what I did was, I can always show you equations, but that means nothing, right? Equations are pretty. But I always want to know what it's like in real life. So what I did is with my photo of the lake around the corner, I said, okay, if I've got a point that it's coming from, that I say that the incident ray is at 30 degrees, how much of the incident light is actually being reflected back to me? I have a lot of assumptions, obviously, seen here. Obviously, my distance to my camera and the height of my camera is not going to be correct, as it is a back of envelope calculation. And assuming that the light coming from the sun is actually unpolarized, I calculated that it's a 14% of that light is actually being reflected back to me. That is, if assuming I've done my calculations correct, of course that could change. And also I couldn't remember if I put my Polaroid lens on or not, so that also might have changed. So in conclusion, reflection occurs in many different ways. There's three main ones that I told you, but I spoke about two, diffusive and specular. And this is actually dependent on the type of the reflecting surface, so how smooth or how rough it is. And it behaves in a very predictable way by the law of reflection. And using basic geometry, so trig and sine functions, you can actually explain the behavior of light between the different medium. And thank you. Yay, everybody understood it.
So I have a question.
Of course.
Could you go back to the first slide?
My very first slide? That one?
What's the
Ah, yes. Okay, so that's where it's actually been, it's a mineral thing. It actually have double refraction. After I developed my PDF, I realised it was refraction, not reflection, hence I didn't say it. But it makes it look pretty, so that's why I put it in. Caustics, that's when you've got the light beam comes in and interacts with a curved surface, and it either refracts or reflects, and it causes this envelope of light to occur. So it's just that kind of, those weird shapes. So if you put your cup in front of a light or something, you get all these wonderful structures that occur.
The first one is a soap.
Soap bubble, yeah, soap bubble.
That would be like thin films, right?
Yep. So yeah, why it gets that multicolored is that you're getting double reflection off two surfaces, thin surfaces. So you got the first one initial and then the second one, which can give you all those wonderful colours. So, and people probably recognise that, that's PI. So, yep. It's when you walk out. So, yeah, I took the photo a couple of days ago.
Okay, thank you.
All right, thank you guys.